Hi, welcome to your Statistical Process Control online classes. My name is Dr. Diaz, and in this inaugural class, you'll be introduced to some of the basic topics, definitions, and terminologies used in statistical process control. I hope you all enjoy this fantastic journey that we are about to begin through one of the most important areas of real-life engineering. Let me start by highlighting the objectives of this first chapter. First, I will introduce the base concepts in statistical process control. Then, we'll define common terms used in statistical process control, such as quality, process, and control. Next, we'll learn how to distinguish between design quality and conformance quality. Those are two distinct aspects of the quality of a product, which have a direct impact on the statistical process control tools to be used. Next, we'll define the basics of quality-related costs. And finally, we'll establish a system that will help us to incorporate a statistical process control mindset and introduce some of their basic tools. Let's start with the basic concepts. You'll be surprised if I tell you that statistical process control is not really about statistics or control. It is actually about competitiveness. Who is going to cross the finish line first? Organizations worldwide, whatever the nature, compete on three base issues: quality, delivery, and price. Those three issues are so important and interrelated that companies build their reputation based on their capability to deliver their products or services faster, with the highest quality and the lowest price possible. This is the goal and the secret behind the success of some of the top companies in the world. Now, let's spend some time trying to define quality. Quality is often used as a synonym of excellence of a product or service. We think immediately about the Lamborghini and the iPhone as examples of excellent products. And that's simply true because these products are well known for their high quality standards. Quality can also be inferred to a product that conforms to certain physical characteristics according to a particularly tight specification. And the word tight here implies that quality is sometimes associated with small variations of the characteristics from product to product. We're going to discuss this in detail later in this course. But a simpler and more elegant definition of quality that we are going to adopt from now on is in terms of meeting the requirements of the customer. This is my favorite one because it ties up the concept of quality to the expectations or needs of the customer. We will also have a chance to look at this more closely later in this course. Let's talk a little bit about the philosophy behind quality control. Although the implementation of comprehensive quality control strategies is becoming essential to business survival nowadays, most of the quality managers has been trying to answer the question, have we done the job correctly, in order to guarantee that their product conforms to certain quality requirements. But it's easy to show that this is not quite quality control, simply because those strategies are mostly based on detection of quality issues in the post-production phase, when the product is ready to go to the customer. This strategy is not the best one because it involves the most expensive and time-consuming tasks. A better way to look at this is if we can prevent the generation of errors and waste throughout the entire manufacturing process by asking the same question differently. Can we do the job correctly? Trying to answer this question allows a much more cost-effective control because we are essentially worried about generating the product or service correctly for the first time. This approach has huge implications on statistical process control methods and tools we are going to learn in this course. This also has a lot to do with the type of process we are dealing with. In order to determine the actions necessary to improve quality, we need first to understand what a process is. A process is the transformation of a set of inputs, which can include materials, actions, methods, and operations, into desired outputs in the form of products, information, services, etc. The output from a process is what is transferred to somewhere or to someone, in this case the customer. And currently, the goal of the quality manager is to produce an output that meets the requirements or expectations of the customer. That's why defining, monitoring, and controlling a process is so important if we want to improve quality. Some examples of well-known and easily understood processes include the process of drilling a hole, the process of filling cans with beverage, and the processing of a chemical component through polymerization. Some of the processes cannot be easily understood, such as servicing a customer, delivering a lecture, storing a product, and inputting to a computer are some interesting examples. Once the process is identified, we need to define the scope, which is done through the CPOC chart. CPOC is the abbreviation of suppliers and inputs, outputs, and customers. And the CPOC chart visually describes the relationship among these elements. In this chart, the voice of the customer can be used as a feedback channel to update the output requirements and improve the process. Another feedback channel can be created through the appropriate documentation of the process definition, inputs, and outputs. This documentation is what we call the voice of the process, and it will allow the collection of reliable data about the process. With that, statistical process control analysis can be performed, and actions can be taken to improve the process to prevent failure and non-conformance with the requirements. Now, let's go through the definition of control. Control usually refers to measurements of the performance of the process and the application of corrective actions where and when it is necessary. It naturally implies that the process is out of control, and by applying some sort of corrective action, we can bring it back to control. Obviously, we must define which metric or metrics we're going to use to determine if the process is in control or not. So, if we know that we could do the job correctly, and that's related with the process capability, we can now try to answer the next question down in the line, which is, are we doing the job correctly? And the answer to this question is related to our capability to monitor and control the process. Now, let's look closely to the difference between quality design and quality of conformance to design. Quality of design is a measure of how well the product or service is designed to achieve its stated purpose. If the quality of design is low, then the product or service will not meet the requirements, or it will meet the requirements only loosely. In this aspect of quality, the specification is a major feature. We should understand the specifications as a complete description of all aspects that must be present in a product or service to meet the customer's requirements. Quality of conformance to design, on the other hand, is the extent to which the product or service achieves the specified design. Data recording for inspection and evaluation plays a major role in this aspect of quality. This is where statistical methods must be applied for effective interpretation of that data. Now, let's talk about the cost of quality. These costs are a true measure of the quality effort and must be carefully managed so that their long-term effect on the business is a desirable one. Usually, quality costs can be divided into three major groups. The first group includes the prevention costs, which are associated with the design, implementation, and maintenance of the quality management system. These costs should be planned to be incurred prior to the production phase. This group also includes costs with product or service requirement, costs with quality planning, costs with quality assurance associated with the creation and maintenance of the quality management system, costs with the development or purchase of the inspection equipment, costs with training of the quality management team, and miscellaneous costs associated with travel, supply, shipping, communication, and other general office management activities. The second group includes appraisal costs, which are associated with the supplier's evaluation of purchased materials to ensure conformance with the specified requirements. The most important costs included in this group are costs with the verification of incoming material, process setup, and includes products or service performance appraisal against agreed specifications. Costs with quality audit to check how the quality management team is functioning. Costs with inspection equipment, and vendor rating costs, which are related to the assessment of all suppliers of both products and services. The third group includes the failure costs, which occur when the product or service fails to reach the design standards. This group can be further split into internal failure costs, in which failures are detected before the transfer of the final product or service to the customer, and external failure costs, in which failures are not detected until after the transfer of the final product or service to the customer. The internal failure costs include costs with scrap, rework or rectification, reinspection, downgrading when the product is usable, but it doesn't meet the specifications and may be sold as a second quality product at a lower price, costs with waste, and costs with failure analysis. Finally, the external failure costs include costs with repair and servicing of returned products, costs with warranty claims, costs with complaints, costs with returns, costs with liability, and costs with loss of goodwill, in which the negative impact on the organization's reputation impinges directly on future prospects for sales. A more intuitive way to interpret each of the costs of quality is through the understanding that prevention costs are the cost of getting it right the first time. This has to do with the process capability, and we're going to show it later. Appraisal costs are the cost of checking it is right, which pretty much matches the description we provided in the previous slide. And the failure costs are the costs of getting it wrong. We'll see that reducing failure costs is one of the main goals of SPC in order to improve the quality of a product or service, keeping a competitive price. The relationship between the three groups of quality costs and the organization's capability to meet customers' requirements is illustrated in this chart. It's important to note that when the organization's capability is low, then the total quality costs are high and the failure costs predominate. This makes sense because we can expect low quality products to result in more scrap, rework, repair, warranty claims, and the organization has to pay for all of it. On the other hand, as we increase the costs with prevention, the organization capability follows the same trend. In other words, the quality of the products increase. and the total costs and the failure costs drop drastically. The main conclusion from this chart is that with only modest investments in prevention to get it right for the first time, and in evaluation and inspection to check it is right, the product quality can be improved, which can bring cost savings to the organization. To summarize everything we've learned in this chapter, we need to start with the general agreement that variability is the root cause of most quality problems. Variation in products, in times of delivery, in ways of doing things, in materials, in people's attitude, in equipment used, in maintenance practice, in everything. We should also acknowledge that SPC is more than simply a toolkit. It's a strategy for reducing variability in the process. And the best way to understand, quantify, and reduce variability is by using some of the statistical tools available. And please don't panic if you are not an expert in statistics. I'm not either, and all the content covered in this course will require only basic knowledge in statistics. You can trust me. Also, we can see that reducing variability through the appropriate control strategy is not enough. SPC requires that the process should be improved continually by reducing its variability. This requires the implementation of a continuous improvement mindset through a proper quality policy, which will provide the environment for teamwork, cultural changes, and improved communication inside the organization. Then we can increase the scope of the questions to be answered that will guarantee that SPC is being applied correctly. As I mentioned previously, we should start by asking ourselves if we can do the job correctly when we're planning the process that will lead us to desired quality levels for the product or service. And this has to do with the definition of the process capability. After we start off the process, we should ask ourselves if we are doing the job correctly, which is associated with the process control. Next, in order to verify the quality of the finished product or service, we should ask ourselves if we have done the job correctly. Remember that in slide 5, I mentioned that it's not correct asking this question first, or only asking this question for an efficient quality control program. But it's perfectly reasonable if we try to answer this question for quality assurance purposes. And lastly, we should always ask ourselves if we could do the job better. This is a very important question if we really want to drive towards a continuous improvement mindset. In SPC, whatever the action or decision we take to understand and control a process, it should be based on numbers and information. Most of the information comes from recorded data, and we should be able to present this data in charts that will help us to understand what's going on with the process. Some of the most used charts in SPC are the process flow chart, which is useful to give us a clear understanding on how the process is done. We have the check or tally chart, which can be used, for example, to count the frequency of defective parts in a specific process. We also have histograms, which provide a good visual representation of variations occurring in a process. We have graphs in which we can represent the variations in a time series. We also have Pareto analysis charts, which are useful to tell us on which problems we should focus first. We have the cause and effect diagram, which are used to identify the cause of the problems. We have the scatter diagrams, which can be used to understand what is the relationship between several factors in the process. And we have the control charts that can help us to figure out which variations we should control and how. And with that, we finished chapter 1. Thanks for watching, and I'll see you in the next video.